Hello everyone, this is just a quick video covering the final few slides and examples from last Saturday's lecture. I forgot that there were a few more examples that we didn't get to go over in class, but I thought they would be helpful when working on your homework and studying for next week's quiz. So as a reminder, this is talking about analysis of hypothesis tests. We talked about how when we make a choice as to whether reject or fail to reject the null hypothesis, there are the possibilities that we make errors. In particular, a type 1 error is when we reject the null when we really shouldn't. So when the null is really true and we reject it, it's a type 1 error. That's denoted by alpha. And then the other error is a type 2 error. That's when we fail to reject a false null hypothesis. That's usually denoted by beta. So the vocabulary here, a type 1 error is made when a true null is rejected. The maximum accepted conditional probability, given the null hypothesis is true, of making a type 1 error is alpha. Now, the p-value tells us the actual probability of making a type 1 error. So if we're using the p-value approach for determining whether we reject or fail to reject a null hypothesis, we know more about what is the likelihood that we've made a type 1 error. Now, a type 2 error, like I said, is when a false null hypothesis is not rejected. That's denoted by beta. And also, we talked briefly about the power of a hypothesis test. That's the probability, which is 1 minus beta, of rejecting a false null hypothesis. That's what we'd like to have fairly high. Given the null is false, I would like to correctly reject it. Usually we'd like to have power at least 80%. So let's look at a couple of examples here. A stats professor has observed that for several years, about 13% of the students who initially enroll in his introductory statistics course withdraw before the end of the semester. A salesman suggests that he try a statistics software package that gets students more involved with computers, predicting that it will cut the dropout rate. The software is expensive, however, and the salesman offers to let the professor use it for a semester to see if the dropout rate goes down significantly. The professor will have to pay for the software only if he chooses to continue using it. So the first question is this a one-tailed or two-tailed test we're going to perform here? Well, in reality, it depends who's performing the test. If I were the professor, I would perform a two-tailed or two-sided test because I want to be more conservative. Recall that a two-sided test will always reject the null hypothesis less often than a one-sided or one-tailed test. The reason the professor would want to do this is that if he makes a type 1 error, he says, oh, this software does lower the withdrawal rate. When it really doesn't, he's paid for all this software that's very unnecessary. So he'd like to avoid doing that. Now, if I was the salesman, I would use a one-sided test because then you're more likely to reject the null that it has no effect, and therefore the salesman would get a sales. So it depends on which perspective you're going to work from. We'll use a two-sided test here. So to write the null and alternative hypotheses, we have to remember that the null and alternative hypotheses are always statements about a population parameter. In this case, it's about a population proportion. So our null is that the proportion of students who withdraw is 0.13, and our alternative, H1, is that P is not equal to 0.13. So this is a two-tailed test. In this context, explain what would happen if the professor makes a type 1 error. Well, I already kind of mentioned this. A type 1 error, this would be rejecting a true null hypothesis. So in this case, the software has no effect. The withdrawal rate is still 0.13, and the professor has erroneously determined that the software is effective, and therefore the professor will end up paying for software that will do nothing to affect the overall withdrawal rate in this course. Now, how does that compare with a type 2 error? Well, a type 2 error is when we fail to reject a false null hypothesis. So in this scenario, the software does provide a benefit to the students. It would lower the dropout rate, but the professor fails to notice that. Now what happens there, the professor's not out any money, but he hasn't improved his course at all, and therefore he's missed out on a good educational opportunity for his students. And what is meant by the power of this particular test? Well, this would be the likelihood of the test determining that the software works if in fact it does. Right? So we'd be able to pick out and correctly reject a false null hypothesis. So if the software actually does lower the withdrawal rate, then the test would want to pick it out. So let's put some numbers to this problem. Initially, 203 students signed up for a stats course. They used the software suggested by the salesman, and only 11 dropped out of the course. Now the question is, should the professor spend the money for this software? Support your recommendation with an appropriate test. Well, we talked about performing a two-sided or two-tailed test. So this is a one prop z-test, as your calculator calls it. We'll take alpha as being 0.05. So this is a 5% level of significance. Now, before we do any calculations, we should verify that the assumptions we're going to need are satisfied. So our p-hat is 0.054. So in this sample of 203 students, we have about a 5% dropout rate. Now, in order to perform any inference, we need to have several assumptions met. First is that n is at least 30. That's met. Since this is estimating a proportion, we'd like to expect at least 10 successes and 10 failures. In this case, a success would be someone withdrawing. So if the null is 0.13, that means that out of 200 students, you'd be expecting more, at least 20 to withdraw. So in that case, we do have 10 expected successes at least, and of course we'd have 10 expected failures as well. The independence assumption might be violated here because this isn't necessarily a random group of students. It's 203 students from the same school who have enrolled in the same stats course. So that independence assumption could be brought up in our post-work analysis. So typing everything into the calculator, performing a one prop z-test, we get a p-value is about 0.0013. Now, since our p-value is lower than our predefined value of alpha, 0.05, we end up rejecting the null in favor of the alternative. That means that there is some statistically significant evidence at a 5% level of confidence that the software is effective at lowering the withdrawal rate for the statistics course. Now, what does the p-value itself mean? We always have to remember the p-value is talking about the likelihood of getting our results or results more extreme given that the null hypothesis is assumed to be true. So if the true withdrawal rate is 0.13, we would see results like we obtained in only approximately 0.1% of random samples of size 203. So that's why this results in us rejecting the null, because this is a fairly rare occurrence. And so we therefore believe that our original assumption, our model of the world, is incorrect. One final example. In the 1960s, census results indicated that the age at which American men first married had a mean of 23.3 years. It is widely suspected that young people today are waiting longer to get married. We want to find out if the mean age of first marriage has increased in the past 50 plus years. So suppose a simple random sample of 40 men who married for the first time last year is taken, and the average age is found to be 24.2 years with a standard deviation of 5.3 years. Does this evidence support the claim that the mean age of first marriage has increased? Explain. All right, so since this is a question concerning population means, we'll be looking at performing a one sample t-test, or as our calculator calls it simply, a t-test. We will choose our default alpha equals 0.05, so a 5% level of significance. And the idea here is we're looking for evidence that the mean age of first marriage has increased. So we'll take as our default null hypothesis that mu is still equal to 23.3 years, so there'd be no increase. The alternative is that mu is greater than 23.3 years. So this is a one-sided or one-tailed test. So I should understand that my choice of performing a one-sided test will have some effect on whether we ultimately reject our null hypothesis or not. This is a less conservative test than if I had done a two-sided test. So our sample data we're given is that the sample mean is 24.2 years, the sample standard deviation is 5.3 years, and the sample size is n equals 40. So once again, in order to perform any actual inference here, any statistical test, we need to determine whether or not we've met our assumptions for using the t-distribution. So sample size is large enough, greater than 30. We should know here that the t-distribution does require us to have some knowledge about the population distribution being at least approximately normally distributed, but we have no information concerning that here. And n, while greater than 30, is not much larger than 30. So therefore, we might reflect a little bit at the end about whether or not all the assumptions were truly met. Specifically about whether or not the population distribution of age of first marriage happens to be close to unimodal and symmetric. So we'll just assume that we've met any of the assumptions we can't prove, and therefore we'll find our test statistic in this case is going to be x bar minus 23.3 all over 5.3 divided by square root of 40. So what we know is that this test statistic, t, happens to follow a t-distribution with 39 degrees of freedom. It's always one less than the sample size. Our p-value, when we plug this into the calculator and perform a t-test, is approximately 0.145. Now, since our p-value is larger than our alpha value of 0.05, we conclude that we do not have statistically significant evidence, at least at a 5% level, to claim that the mean age of first marriage has increased. Now, what we have not done is proven that it has not increased. We just don't have evidence that says that it has increased. So remember, we never confirm or prove the null. We just fail to reject the null hypothesis. Okay, so hopefully those examples will help you when completing the homework. And if any further questions, also check the Blackboard page for the last set of group work problems that we did not have time to complete in class. Those solutions will be posted briefly after this video is posted. Thank you, and see you next week.